Good evening, everyone. This is JEE Advanced lecture number 13, I guess. And we are dealing with EMI or electromagnetic induction. I hope I'm audible and visible to all of you. Yes or no?
Yes, sir.
Okay. Now, in the previous class, we had dealt with what I call as dynamic EMI. And we had seen what happens if a rod is moving or rotating in a uniform magnetic field, and we had seen that it can be replaced by a battery. Yes or no? We had solved some questions on that as well, and I think if I remember correctly, I had given you a question where it was non-uniform magnetic field and the rod was rotating, and in a particular position you were supposed to find out the EMF induced. Yes or no?
Yes, sir.
Did you try that question? Did you get any answer for that question?
Sir.
I think this was the question. We had a rod of length L rotating with an angular speed omega about one of its end, and it was placed in a non-uniform magnetic field. Remember, whenever a infinite wire is given to produce a non-uniform magnetic field. And we are supposed to find out the EMF induced between the ends of this rod in this particular position. Remember, if I change the position, the answer would be slightly different, which would be the next question that would be coming in. Once you get this, you could tell me what that answer would be. So, did you try this question, bacha? Or shall I do it on my behalf?
I will try, sir.
Okay, you want to try? Remember, beta, it might so happen that the same question will come in your exam. Okay, and if a question of this nature comes, probably it would be in a comprehension type. It would be having more than one question attached to it. So, or it may be in the multiple choice section where they ask you different things. They might give you 2 or 3 positions. One might be horizontal, the other might be vertical, and you never know. Okay. So, give you 2 minutes. I hope you can do this, right? I'm hopeful. 2 minutes. Okay, then how this question has to be done? Remember, this rod is rotating in a non-uniform magnetic field. Do we understand this? And therefore, we just cannot simply apply the formula of half B omega L square because B is not constant. So what we do? Very simple. We'll have to apply the technique of integration. This distance is given as A. I take a point on the rod at a distance x, whose element length is dx. Remember, I told you how we derived the original formula. Then, how do you find out the EMF induced in this part? It is V cross B dot dl. Yes or no? Small
Yes, sir.
potential difference. Magnetic field will be mu naught I upon 2 pi into x plus a. Yes or no?
Yes, sir.
Its angular velocity will be x into omega. Yes or no?
Yes, sir.
Multiplied by dx, and you just integrate this x from 0 to L, and you will get a result of this nature. Do we understand this?
Yes, sir.
So I would request you to draw the diagram and just write the result so that if this comes, you would be able to remember this. Got it now?
Yes, sir.
Shall I move further ahead? May I ask where did you commit a mistake, or what was the part that you could not understand in this
What, sir?
question? What was the part that you could not understand in this question, beta? That you could not solve on your own?
No, sir. Calculation mistake किया sir मैंने.
Calculation mistake. Okay, you must guard against these calculation mistake. As I told you, they could give you different positions. They could give you different position and they could ask you in which position, what is the answer. So if I talk about any general position theta, you can remember this formula. Similar thing will happen just because of the orientation. This factor of cos theta is coming everywhere. Do you understand this?
Yes, sir.
It is coming just because of this angle thing. So this is the answer if it is at an angle theta. Okay. Can we move further ahead?
Yes, sir.
Okay, then this question, I think you would have seen this question somewhere. And there are many questions of this type that you might have come across in EMI. If you can do any one of those, most of the questions would be of similar nature. In some questions, the rod would be given a velocity and then you will have to find out after how much time it will stop, what is the distance traveled by the body. In some questions, there might be a force which is trying to pull the rod and then they will ask you what is the terminal velocity in that case. Such questions are given in SCV. I hope you have gone through them. Yes or no? 5 or 6 or 7 questions of this nature are given in that particular book. So you can try it from there. This is one of those questions. A rod of mass M and resistance R. So the rod also has a resistance. Now the rod may not have resistance. There is a resistance capital R as you can see. So it doesn't matter. There is a resistance in the circuit. A rod of mass M and resistance R is placed on a fixed resistance less smooth rails close by resistance R and is projected with an initial velocity U. Find its velocity as a function of time. This is one of those questions. There are many questions. In one question, you will start applying a constant force and then they will ask you what is the velocity as a function of time and what will be the terminal velocity and all those things. You can do any one of those. You should be able to do the rest of these because the concept is exactly similar. Do we understand this?
Yes, sir.
So have you done this question before?
No, sir.
No, sir. Then this is the time where you can try this question. Magnetic field is given as B. Initial velocity is U at time t is equal to 0. Mass of the rod is M. Resistance of the rod is small r. For making the question similar, you can neglect this resistance small r and only take the bada resistance capital R, or you can take capital R plus small r as Rx or something. Doesn't matter. That is not going to make much of a difference to the entire question. I'll give you 2 minutes to go through this and solve it. And I hope that you can do this.
V equal to UE power minus KT.
That is absolutely correct. And I'm very impressed that you could get this. So basically, you assume that the velocity at any time is V. Then
Yes,
in
sir.
that case, you can find out the induced EMF. Induced EMF will be equal to BVL. Yes or no, beta? Then you
Yes, sir.
divide it by the resistance. Take it anything, doesn't matter. Now, once you have the current in the circuit, bacha, what you can do is you can find out the force on this rod. Force on this rod will be ILB and that would be deaccelerating the rod. Therefore, minus M into dV by dt. I is BVL by R. Then you can solve this equation. This is a simple equation where you will get dV by V is minus a constant times dt. This constant B square L square by R plus R into M can be written as K. You can simply now integrate these equations and get the answer, and your velocity will vary exponentially. That means it will actually never become zero theoretically. After a long time, it will become zero. Do we get this? Yes or no?
Yes, sir.
Did you get the correct value for K? That is the only thing that we are concerned with. Did you get the correct value of K?
Yes, sir.
Yes or no?
Yes, sir.
Great. As I told you, there are different variations of this question, and this is one of the variations of the question. Now, if this question comes, this could be a part of the stem. Could have 2 or 3 questions coming in the stem, and this is the question that could be the next question in the stem. In the above question, find the force required to move the rod with constant velocity v, and also find the power developed by the external agent. Now, I want it to move with a constant velocity v. How much force should I apply? And what power would be delivered by this force, or obviously external agent, because external agent is going to apply this force. What would be your answer, bacha, in this case? It has to move with a constant velocity. Remember, when it is moving with a velocity v, electromagnetic force starts to act on it, and it will try to stop it, because it will oppose the cause of production of EMF. So what will be the external force that will be required to move it with a constant velocity? Remember this. You must be knowing this. Yes or no?
Yes.
Whatever force is due to the magnetic field because of electromagnetic induction, the same force must be applied in the opposite direction to make it move with a constant velocity. Yes or no?
Yes, sir.
So your force will be equal to that d square L square V upon R plus R. To find out the power, you can simply multiply this force with velocity F dot V, and you will get this power, and this power will be coming as I square into R plus R. Basically, this power will be dissipated in the circuit in the form of heat energy. So whatever power you are putting in, same amount of power would be dissipated out. Energy cannot be created, nor it can be destroyed. It can only be converted from one form to another. Here, the energy applied by the external agent is getting out uselessly in the form of heat. Do we understand this?
Yes, sir.
Now, as I told you, there are different variations of the question, different stems that you can have. Here, the third stem, as I told you, there are different variations. In the above question, if a constant force F, as I told you, so constant force F is applied on the rod. Find the velocity of the rod as a function of time, assuming that it started with 0 initial velocity. I hope you understand the question, bacha. The rod was at rest initially, and now I start applying a constant force F. What will be the velocity of the rod as a function of time? That is your question, and I'll give you 1 minute to solve it. I hope you can do it. It's pretty simple and straightforward. So, what is different between this question and the first one? Nothing. Initially, it was given as initial velocity u. Here, the velocity is 0. Instead of that, I've applied a force. So, what will happen is you just need to frame the equations of dynamics for this body, and the equation of dynamics is very simple. M into dv by dt, M into A will be equal to F minus L ILB. Yes or no? In the previous case, F was missing. That is the only thing. Yes or no?
Yes, sir.
I is same. Everything is same. K is same. You just have to integrate it from here to here. Yes or no? And
Yes,
you
sir.
will get your answer in a very famous form. And you might have seen this form coming many ways. This is the form in which the charge on the capacitor varies. Yes or no, when the charge on the capacitor is 0? Yes or no?
Yes,
This
sir.
is the same way this question has come. Yes or no? Do you understand this, beta? This was Q naught. Yes or no?
Yes, sir.
Oh, sorry, Q infinity. This is Q infinity, V max. Yes or no? This
Yes,
is the terminal velocity of the body. Because after some time, force is constant, your velocity will keep on increasing, and at one point in time, your dragging force, your external force, and the force applied by the magnetic field which is trying to stop it will become zero, and the body will attain terminal velocity. Do we understand this? Same question of charging of a capacitor. Time constant here is m by k. Do we understand this, beta?
Yes, sir.
Q infinity here is f by k. Same thing. There, here we are applying force. There we were connecting it to a battery, nothing else. Same thing is happening. These two questions are equivalent. So this is how you can remember things, beta. Taking the equivalence that this question and the other question are exactly same. Now comes this one, and I hope that you would be able to solve this one for me. A rod PQ. This is the rod PQ of mass M and resistance small r. The resistance might not be there, doesn't matter. Is moving on two fixed resistance-less smooth conducting rails closed on both sides by resistance R1 and R2. So you have two branches here. Find the current in the rod at the instant when its velocity is v. Remember, whenever a question of this nature comes, remember it is not a question of EMI. This is a question of what? This is a question of electric current. Do we understand it? Yes, this is not a question of EMI at all. This is a question of electric current. Since you have understood that this is a question of electric current, then you must be able to tell me the answer straight away. Then you must. Yeah, so tell me the answer straight away, bacha.
2 minutes of time.
It's a very simple question of electric current. You can do this in 10,000 different ways. 10,000
Yes, sir.
exact.
Got it, sir.
Got it, sir. So check it, sir. It's very simple. You can do it in by different ways. R1 and R2, these two resistances are in parallel. Then it is in series. Then you can
Yes,
find
sir.
the total current. Yes or no?
Correctly, yes,
You
sir.
can apply nodal theorem as well. You can find out the resistance in current in R1, current in R2, and add those two currents. You will get the current in R. Yes or no, beta?
Yes, sir.
Now, comes this question, and this question is a supplement of the previous one. Now you see how things have changed. Up till now there were resistances. Now I have a capacitance. And in one question you will have inductance, but we are not done inductance now. So I have the same rod of length L. I think length is given. Placed in a magnetic field B. One of the resistances R. The other is replaced by a capacitor, and I apply a force on the rod. And the rod has an initial velocity V. Find the velocity of the moving rod as a function of time t. At time t is equal to 0, its initial velocity is v. This is how questions are framed in a JEE. You can do this, nothing like it. No question will ever come and trouble you. I'll give you 2 minutes to do this. I guess you might not have seen this one.
1 minus e power.
Right. So basically, again, the equation is same, right? F minus ILB is equal to M into A. Do we understand this?
Yes, sir.
I is the current in this rod. Now, how do I find the current in this rod? Remember, this rod does not have any resistance. So the EMF developed will be B into V into L. Yes or no?
Yes, sir.
Now that same potential difference is applied across this resistor. This same potential difference is applied across this capacitor. So that will is equal to I1R. That will be equal to Q by C. Yes or no?
Yes, sir.
Now, if I apply junction law at this point, this total current I will be equal to I1 plus dq by dt. Yes or no?
Yes, sir.
And you just put the equation and you get the value of I. Once you get the value of I beta, this is exactly same as what we had done in the previous case. Yes or no?
Okay, sir.
Got it, beta? Once you get the value of I, you put it in that same equation, and this is exactly same as what we had done before. Yes or no?
Yes, sir.
Do I need to explain this?
Sir,
Do I need to explain what is happening here? Or have you understood this?
explain, sir.
So I put this F minus ILB is equal to M into A. Yes or no? I have just put the value of I from here, and I have put this value of I in this equation. Got it?
Yes, sir.
And we get whatever is there. And we can now simply integrate this. Yes or no?
Yeah, sir.
Once you get to this position, you can now simply integrate this. Got it?
Yes,
So
sir.
the main heading, main thing of this question is to get the value of I. And how do you get the value of I? You add the current in both the branches I1 and dq by dt. I1 into R is BVL, and BVL is again equal to dq by dt. That is the main point of this question. Shall we move ahead?
Sir, wait, sir, I will note this.
Yes, beta?
I will note it, sir. Just wait.
Okay, you want to note it? So let me make it a bit smaller so that you can note the entire solution together. So I'll just make it a bit smaller, and I hope that you can get the entire solution in one sheet. Might look a bit smaller, but I hope that you would be able to understand it. Got this?
Okay, sir. Just wait.
It might just look a bit smaller but in size, because okay, I think it's there now. Okay, so total current I is I1 plus dq by dt. I1 is BLV by R. dq by dt is dq by dt is d by dt of BLV into dt. BLV into C. So it is d by dt of V, so it becomes A here. You can remember these things. You have done enough to solve this question. I'll give you 2 minutes to note this down. Okay, then we move on to the next question, and the next question looks like this. It is somewhat different to the question that we have done before. A rod PQ of length L is rotating about the end P, then angular velocity omega. Now remember, there is no magnetic field here. You must be surprised how EMF is induced. There is no magnetic field. Due to centrifugal forces, the free electrons in the rod move towards the end Q. Wow. And an EMF is created. Do you understand why this EMF is getting created? It's a conductor, it is rotating, and because of rotation of the centrifugal forces, the electrons are moving towards the end Q, and an EMF is created. So basically, P point will be at a higher potential, and Q point, because electrons have moved there, will be at a lower potential. What is the induced EMF in this case? There is no magnetic field. So it is not a question of dynamic EMF. But here EMF is induced because of centrifugal forces. I'll give you a minute to think about it. See, it's very simple. Because of this accumulation of electrons, they will create an electric field. Because of this electric field, the charges, the electrons will experience electrostatic force. And when a steady state is reached, these electrostatic force must balance the centrifugal force, otherwise the electrons will keep on moving. In steady state, they will not move. So m omega square x, where m is the mass of the electron, will be equal to E into or Q into E, where Q is the charge of the electron. Are you getting my point, beta?
Yes, sir.
From here, you can find out the value of the electric field. Electric field E becomes m omega square x by Q, where Q is the charge of an electron. You multiply this by dx and you integrate it from 0 to L. You will get the potential difference between the two ends of the rod, and that will be equal to m omega square L square by 2 times E. Did you get this one, bacha? Now,
Yes, sir.
any problem? Please let me know.
Okay, sir. Okay, sir. Clear, sir.
Clear?
Clear, sir.
No problems with this one?
Yes, sir. I also got same, sir.
You also got same, sir. Well done, sir. I must congratulate you if you have got. You want to do more questions on this motional EMF?
Sir?
You want to do more questions on this motional EMF?
Yes, enough, sir. Next topic.
Or shall I move on to the next topic?
Next topic.
Okay, so motional EMF, let us stop it here. Let us move on to the next topic. And the next topic is what happens if you don't have anything moving? If you don't have anything moving and you place a coil in a magnetic field and you just vary the magnetic field with time, if you do that, then also an EMF is induced in the coil, and this induced EMF is explained by the concept of induced electric field. So wherever in space you have a magnetic field that changes with time, it may increase with time, it may decrease with time. Electric field is induced in that space, and because of this induced electric field, you can have potential difference between any 2 points in this space. But remember, this induced electric field is different from the electrostatic field that an electrostatic charge creates. The field created by electrostatic charge is conservative in nature. If you move in a closed loop for the electrostatic field, E dot dl ka integral over the closed loop is 0. But for this particular field, which is the induced electric field, this integral is not 0. In fact, it is equal to the induced EMF, or it is equal to minus d phi by dt. Do we understand this?
Yes, sir.
Therefore, if you move the charge in a closed loop in this field, the work done would not be 0. You have to do some work in this field if you move the charge in a closed loop. Also, potential has no meaning in this field, because if you go from point A to point B in different paths, you will have different potential difference. So potential difference here for this particular field will depend on path. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
So potential difference has no meaning in different paths. You will have different potential difference. This field is different from electrostatic conservative field. F is equal to QE is still valid. in this type of field. Will you remember this?
Yes, sir.
Okay. Now, whenever you get a question of such nature where magnetic field is changing with time, you will always find that this magnetic field will vary or will change in a cylindrical space. Please note this. Whenever you have a question of changing magnetic field with time, 99.9% cases, that question would be framed in a cylindrical space or on inside a solenoid where this magnetic field will change with time. In that case, whenever a magnetic field is changing in time in cylindrical space, the electric field which is induced will be moving in circles. Electric field will be moving in circles which are concentric with the cylindrical space. Do we understand this, bacha?
Yes, sir.
As you can see here in the first description, the electric field which was shown here, as you can see, the electric field which was shown here is moving in circle, and this is the magnetic field. And remember, this magnetic field is varying in a cylindrical space. This will give rise to an induced electric field which will be moving in concentric circles. Do we understand this?
Yes, sir.
Now, they might give you a question of finding out the value of this electric field which is moving in circles. I will just show you how it is done and you must remember the results. So the question would be of this nature. You will have a magnetic field which is changing with time in a cylindrical space at some rate. Then you will have to find out the electric field as a function of R, where small r is the distance from the center of that cylinder. There will be three different types of point where you will have to find out this electric field at any point inside A, at any point on the circumference B, and at any point outside, that is C. Do we understand this, bacha?
Yes, sir.
Three types of points: inside points, circumference point, and outside point. So how do you do this? You just find out the line integral and you remember these things, and you remember this graph for this. I hope you would have seen this and you would understand how this has been accomplished. Do we understand this better, how this has been accomplished?
Yes, sir.
For any point inside, you take the integral of E into dl, it will become E into 2 pi r. That will be equal to d phi by dt. Area is constant into dv by dt. So you will get electric field as alpha r by 2, where alpha is the rate of change of magnetic field with time. So you can see this electric field is directly proportional to r, small r. If you want to find out the electric field on the circumference, you just put in place of small r, capital R, and that will be the maximum possible electric field, capital R into alpha by 2. Are you seeing it in your notes, beta?
Yes, sir.
Then you will have points which are outside this cylinder. Now what happens for outside this cylinder? Integral of E dot dl becomes E into 2 pi r. But when you find area into dv by dt, area it will only have that much flux which will be coming in this area which is enclosed by the cylinder and not the entire area, because outside the cylinder there is no magnetic field. So when I take area, it will be pi into capital R square, and when you find out the result, E would be inversely proportional to R and it will decay like this. So you will have maximum electric field appearing on the circumference. Yes or no?
Yes, sir.
Okay. Then comes a small question based on this. Similar question has come in JEE, if I remember correctly. I think maybe the same question, I don't know. So this is an example from the sheet itself. For the situation described in the figure, the magnetic field changes with time. Remember, it's a cylindrical space. According to the equation, some equation is given. Calculate the force of an electron located at P2 at time t is equal to 2 seconds. What are the magnitudes and direction of electric field at P1? P1 is here. Time 3 seconds. And the distance is 0.02 meters. I hope you can solve this. I'll give you a minute to do this. So how you got to do this? You just have to find out the electric field at any point outside. You already know the formula for this, right?
Yes, sir.
E into 2 pi r multiplied by pi r square. You just have to find out the rate of change of magnetic field with time. You find the derivative of B. Yes or no? So
Yes,
you
sir.
will get a formula of this nature. Capital R square by 2R 260 square minus 80. To find the force on the charge, you just multiply it by the charge. Multiply the electric field by the charge of the charge and you get your answer. You just put the value of T as 2. Getting my point, beta? The only thing that might trouble you is to find out the direction of this force. To find out that at time t is equal to 0, you have to find out whether magnetic field is increasing or decreasing. If the magnetic field is increasing, electric field has to decrease it. Electric field is created by positively charged moving moving charge. So you can from there you can find out the direction of current, and the direction of current should be such that it should oppose the increasing field. So it should create field in the outward direction. From there you can find out the direction of current. Direction of current is same as the direction of electric field, and the force on the negative charge, negative electron would be opposite to the direction, and hence you will have the force acting downwards. Do we understand this, beta? What I have said?
Yes, sir.
That was it. The first part of the question was this. The second part was still simpler. You just have to find out electric field at any point inside. You just put the formula for any point inside, R into alpha by 2, where alpha was the rate of change of magnetic field. Instead of writing it as alpha, it is better that you write this alpha as dB by dt. Are you getting my point, bacha?
Yes, sir.
So you will not make a mistake in the next case. So magnetic field at any point inside is dB by dt into R by 2. Magnetic field at any point outside is R square by 2R into dB by dt. Will you remember this, beta? Yes or no? No or yes?
Yes, sir.
Okay, so I hope we have covered this part thoroughly, and we can now move on to something known as self-induction. Have you heard this term, self-induction?
No, sir.
Okay, it's very simple. Now, up till now, we were dealing with resistances and capacitances. Now, what does a capacitor do? It stores charges. What does a resistance do? I mean, energy is given out in the form of heat. Now, a resistance or a straight wire, if I flow current in that wire, that current will produce a magnetic field, yes or no?
Yes, sir.
But the wire is very thin. If you find out the flux linked with that wire, it would be very small, yes or no?
Yes, sir.
But imagine if I have a wire and I turn it like this, I make loops in that wire. If I make loops in that wire, the wire probably looks something like this. And I hope you can see this. The wire looks something like this. That wire now has an area. So if I flow current in that wire, a flux will be linked with this wire. If the current in the wire changes, the flux linked with the wire or the loop or the coil will change and EMF will be induced in this coil. This phenomena is known as self-induction. Do we see this, beta? Whenever current is flowing in a coil and due to this flux is linked with the coil, when the current in the coil changes with time, magnetic flux linked with the coil changes with time, an EMF will be induced in the coil which will try to oppose the change in flux. I hope you understand it. Yes or
Yes, sir.
no? Magnetic flux will try to induce EMF, will try to oppose the change in flux. This phenomena is known as self-induction. Do we get this, beta? This phenomena is known as self-induction and this property is known as self-inductance. Do we understand this?
Yes, sir.
Okay. Then how do you represent this inductance of a coil? I mean, you represent resistance by, you represent resistance by jig, 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 jig. You represent inductance by a coil like this. Do we understand this, beta?
Yes, sir.
Okay. So now you have three elements in a circuit. You have a resistor, you have a capacitor, and you have the third term. The third term is your inductor. Getting my point, beta?
Yes, sir.
How do I see? Okay. The third term is the inductor. And how do I find the inductance of this inductor? If I keep the current through the coil constant, I flow a current in the coil that will create a magnetic field. Because of this magnetic field, a flux will be created. But if the flux does not change, there will be no EMI. The total flux link will depend on the current of the coil, or N phi will be proportional to I, or N phi is Li, or your L becomes total flux divided by I. This L, this constant, is known as the coefficient of self-inductance. Do we get this, beta?
Yes, sir.
Okay, this is how we find out the self-inductance of a coil. It is given in your sheet. I hope you can see this. Yes or no?
Yes, sir.
The SI unit is Henry. You know this. Yes or no?
Yes, sir.
Now, if I have this current changing with time, an EMF will be induced in the coil, and that EMF from the diagram you can see will be equal to minus L di by dt. This L is again known as the self-inductance of the coil. Yes or no? No, yes.
Yes, sir.
So you can define the self-inductance of a coil by two ways. You can either define it by the flux linked with the coil, or you can define it by the EMF induced in the coil. Do we understand this?
Yes, sir.
Similarly, if you are supposed to find out the self-inductance of a coil, what do? You do very simple things. You first of all flow a current I in the coil, then you find out the magnetic field, then you find out the flux, and you equate the total flux equal to Li. From there, I will get cancelled and you will get the value of L for a plain coil with area A. If it is a square, if it is a circular coil, area will become pi r square. If it is a square coil, area will become a square. If it is a rectangular coil, area will become a into b. You can find out the self-inductance of a plain coil. This self-inductance that we have found here is the plain inductance of a circular coil. Do we understand this, bacha?
Yes, sir.
What I have done here is instead of a, I have put pi r square. Do we understand this?
Yes, sir.
So if someone asks you to find out the inductance of a square coil instead of capital A, just put A square. I hope you can do this. Yes or no? No, yes.
Yes, sir.
Yes, sir. Similarly, sir, you can find the self-inductance of an infinite solenoid. You just remember this formula. The concept remains same. You flow a current I in the solenoid. Then you find out the magnetic field. Because of this magnetic field, you find out the magnetic flux. You find out the total flux equated to Li, and you will get the answer like this. Yes or no? No, yes.
Yes, sir.
You can note this answer from your sheet. Shall I move further ahead?
Okay, sir.
Yes, sir, or no, sir?
Yes, sir.
Now, let us quickly finish this mutual inductance so that in the next class we can deal with questions on this. Now, instead of one coil, when you are having just one coil and you are flowing current in that coil, because of that current, flux is linked in the same coil. And if that flux, if the current is changing, EMF is induced in the same coil. Now imagine that instead of one coil, you have two coils. The first one is known as the primary and the second one is known as secondary. Do we understand this, bacha? Primary and secondary, transformer. Have you heard the word transformer? Yes or no?
Yes, sir.
Something like a transformer. It is not exactly a transformer. You have two coils. So call first coil as number one and number two. Instead of calling it as number one and number two, I'm calling it as primary. Primary and secondary. Now, if I have current in the primary, flux will be linked in the primary. That is known as self-induction. Forget about that. It can happen that because of current in the primary, flux is linked in the secondary coil. Yes or no?
Yes, sir.
But that will only happen depending on the orientation of the coil. If one coil is here and the other coil is 10 kilometers away, nothing will happen in the other coil. Obviously, the coil has to be arranged suitably. Yes or no?
Yes, sir.
We will see that arrangement, how it comes into the picture. But let us now assume that you have a primary coil and then you have a secondary coil and they are magnetically coupled. Do you understand the meaning of magnetically coupled?
Yes, sir.
Magnetically coupled means if you do something with this coil, something will happen in this coil, that is coupling. So if I have current in the primary coil, a flux can be linked in the secondary coil. This phenomena is known as mutual inductance or mutual induction, because if I change the current in the primary coil, EMF will be induced in the secondary coil. This phenomena of induction of EMF in the secondary coil because of change of current in the primary coil is known as mutual induction. Do we understand this?
Yes, sir.
So phi 1 is the flux linked in the primary coil because of current in the primary itself. Phi 2 is the current link, the flux linked in the secondary coil because of current flowing in the primary. Now, the best scenario will be phi 2 and phi 1 are same. Then we call the magnetic coupling to be perfect, but that will not happen. Do we understand this, beta? So here again, you have two cases. In the first case, what we do is I flow a current in the primary and I keep that current constant. So the flux linked in the secondary is N2 into phi 2. N2 is the number of turns in the secondary. Phi 2 is the flux linked in one coil. So N2 into phi 2 will be directly proportional to I1. Do we understand this better?
Yes, sir.
That means N2 into phi 2 will be equal to M, a constant, multiplied by I1. This constant depends on the orientation of the coil. This depends on the geometry of the coil, and it also depends on the material or the medium separating the coils. This constant is known as the coefficient of mutual induction. Do we understand this better? It is all given in your sheet.
Yes, sir.
Now, second case, I am going to change the current in the primary. Because of this, what will happen in the primary is self-induction. Something will happen in the secondary also. EMF will be induced in the secondary. That EMF will be proportional to the rate of change of current in the primary, or I can write d5 by d2, rate of change of flux of secondary will be equal to minus M into di1 by dt. This M is known as the coefficient of mutual induction. Do we get this, beta?
Yes, sir.
Something is happening in the primary, and because of that, secondary is getting affected. This phenomena is known as mutual induction. On what all factors this mutual inductance depends on? Please remember this. There might be a question that comes on this. As you can see, the mutual inductance does not depend on current in the primary and the secondary. Remember it. It depends on the number of turns. It depends on the area of the two coils. It depends on the distance between the coils. Obviously, if the distance is very high, nothing is going to happen. It depends on the coefficient of self-inductance L1 and L2. It depends on the magnetic permeability of the medium, which medium is there. It depends very importantly orientation of the coil and the coupling factor. This coupling factor is nothing but it depends on the orientation of the coil, how these coils are arranged. The maximum value of coupling factor is 1. The coupling factor is 1. Whatever flux is linked in the primary, the same flux will be linked in the secondary. Am I going too fast?
No, sir.
Yes or no?
No, sir.
You are able to comprehend what I am saying here, beta, because we don't have time and we'll have to cover the course. That's why I have to speed up a bit. Yes or no?
Yes, sir.
Okay. Then you can remember these small things. Coefficient of mutual inductance for different types of coils given in your sheet. I'm just showing it to you. If you have two circular coils, you can easily find out what will you do. I gave you a question on this. You will flow current in the outer coil and find the flux through the inner coil. Yes or no? Did I tell you that?
Yes, sir.
Once you do it, you will get the mutual inductance between the two coils. Remember, it is directly proportional to the radius of the inner coil square, and it is inversely proportional to the radius of the outer coil. Do we understand this?
Yes, sir.
Remember this thing. It's a very important result. So now if you have two square coils, the same result will happen. If you have a circular coil out inside a square coil, same result appears. Do we understand this? Yes or no?
Yes, sir.
Am I going too fast?
No, sir.
You'll have to remember these results, beta, because any question which comes on mutual inductance, there are hardly one or two questions which are there which will come on mutual inductance. Most of the question will be based on these concepts. Are you getting me?
Yes, sir.
Now, as I told you, there is something known as the coupling factor. Now, if I bring in that coupling factor, the mutual inductance can be written as K times root over L1, L2, where L1 and L2 are the coefficient of self-inductance of the two coils. K is known as the coupling factor. The value of this coupling factor varies from 0 to 1. If coupling factor is 0, there is no flux linkage. Whatever you do in the primary, nothing happens in the secondary. Secondary is too far away. It is not coupled. Whatever you do here, nothing happens here. If coupling factor is 1, whatever flux is linked in coil 1, you just put the secondary on top of this. The same flux get linked with coil number 2. Do we understand this, beta?
Yes, sir.
You can find out the value of this coupling factor from various things, and you might be given all these diagrams. So just look at these diagrams and see if you can make out the value of coupling factor. In case number 1, what I have done is I have wrapped the secondary on the top of primary. Therefore, the coupling factor becomes 1. Do you see this, beta? Primary, and then on top of that, I have secondary. Coupling factor becomes 1. Are you getting me, beta?
Yes, sir.
In case number 2, primary is here, secondary is here, separated by a small air gap, and therefore the entire flux of primary will not be linked with the entire flux of secondary, and therefore the coupling factor will lie somewhere between 0 and 1. It will not be 0, but it definitely will not be 1. Yes or no?
Yes, sir.
If I put the primary and secondary like this, whatever I do with the primary, no flux will be linked with the secondary, and the coupling factor becomes 0. Similarly, if I put them like this, again the coupling factor becomes 0. Or I can also write coupling factor as flux linked in the secondary divided by the flux linked in primary. Do you understand this?
Yes, sir.
Okay. Then I have these 2 or 3 points that you will note down, and then we would call it a day for today's class. The next class we'll be dealing with questions based on this. If I have inductance in series and inductance in parallel, most of the cases you will have the mutual inductance as 0. So in series, what is going to happen? The effective inductance will be L1 plus L2. Do you understand this?
Yes, sir.
And in case of parallel, if M is 0, that will be the case in most of the cases. 1 by L will be equal to 1 by L1 plus 1 by L2. So this is basically similar to how resistances are added. In series, you add them straight away. In parallel, you take the inverse and then add. Do you understand this, Bacha?
Yes, sir.
There might be a very difficult case, and I don't think this will come because this is most probably out of your JEE syllabus. If mutual inductance is 0, but I've once seen a question coming on this once in one of the JEEs. If mutual inductance is not equal to 0 and they carry current in the same direction, then your effective L will be like this. If they carry current in the opposite direction, your effective inductance will be L1 plus L2 minus 2M. Can you remember this point, Bacha? I've seen once a question asked on this. Okay. Can you remember this, beta?
Yes, sir.
In case of mutual inductance not equal to 0 and they are connected in parallel, this is how you can find out the effective inductance. I don't think they will give a question on parallel with mutual inductance. That is way beyond JEE syllabus. The most they can give is in parallel, is in series. And that too, even that too is not a part of JEE curriculum. Do we understand this?
Yes, sir.
Okay, since we have done this, we can solve a simple question like this and tell me the answer for this. How does the mutual inductance of a pair of coils change when number 1, distance is increased, number of turns is decreased, a thin iron rod is placed between the two coils? Remember, a question of iron rods has come in one of the JEEs. I'll give you 2 minutes to think and give me the answer. First one decreases, correct. Second one also decreases, correct. The only problem was the third one. When an iron rod is placed between the coil,
Maybe it
remember,
increase.
the permeability of the medium increases. Iron rod is magnetic in nature, and therefore the mutual inductance will increase. Do we understand this? Do we understand this, beta?
Yes, sir. Yes, sir.
Okay. Okay. Now let us just wind up this theory on inductor so that in the next class I can just go ahead with problems. So this is the last bit of knowledge that I have to tell you. Similar to what happens in the capacitor, when the capacitor becomes completely charged, it stores electrical energy, half CV square. Do we remember it, bacha?
Yes, sir.
Half CV square. Similarly, when current flows in an inductor, it will store energy in the form of magnetic energy. And how much energy is stored? Half Li square. You must be knowing this, yes or no?
Yes, sir.
Yes or no?
Yes,
This
sir.
energy is stored in the form of magnetic field. Yes or no?
Yes, sir.
Great, sir. Then you must also know that wherever in space you have electric field, you have electric field energy density. Yes or no?
Yes, sir.
Half epsilon naught E square, energy stored per unit volume, yes or no?
Yes, sir.
Similarly, wherever in space you have magnetic field, you have magnetic energy stored per unit volume, which is known as magnetic energy density. Electric energy density is half epsilon naught E square. So what will be magnetic energy density? Epsilon naught in the numerator, so mu naught will come in the denominator. It is B square by 2 mu naught. Do we understand this? Yes or no?
Yes, sir. Understood.
Understood? Yes or no?
Yes, sir.
Well, then we come to an end for this theory part for this particular topic. The next class we'll be dealing with a lot of questions and winding off this topic probably by tomorrow. The next class. What we have done today is we have solved problems on dynamic EMI. We have solved problems on rod moving, different problems. You have find out velocity as a function of time and all those problems. Then we did the concept of induced electric field. Wherever you have a changing magnetic field with time, we have an electric field which is induced. It is non-conservative in nature. We found out the value for magnetic field changing in a cylindrical space. Then we move on to the phenomena of induction. Current in a coil changes, that the current is changing. EMF is induced in the coil, self-induction. What happens in the other coil is mutual induction. We saw the inductance of some simple examples. We'll solve one or two questions on mutual inductance of a wire and a circular coil. We have seen energy stored in an inductor, and we have seen energy density of magnetic field. We'll try to wrap up this chapter tomorrow. Same time. I'll see you. Take care. Have a nice day. If you have any doubts, you can come up and ask me. Else, bye-bye.